But this process here is called differentiating from first principles. This formula here is called first principles, and I'm literally differentiating. I'm finding my gradient function. So the process is called differentiating from first principles. There may well be a question in the exam which says differentiate this from first principles, okay? In which case I want to see this process written out. All right? Is that okay with everyone? Okay. The issue is though, this is quite long, isn't it? This is really long. And particularly when you start looking at x cubes, you're having to like expand everything out and then think about what happens if you cancel. Wouldn't it be nice if there was just a nice simple way of getting from here to here? Okay, in other words, getting from your original function to your gradient function. Okay? Fortunately there is, but there is a bit of work to get there. Okay? So, let's have a look at this. Let's make some space. All right. Okay, this is how it works. What would a to the power of 0 minus b to the power of 0 be equal to?
0. 1 minus 1.
Exactly, 1 minus, oh, sure. Sorry. Okay, what would a to the power of 1 minus b to the power of 1 be equal to? A minus b? Yeah, perfect. Okay, a little bit more tricky. What about a squared minus b squared?
A minus b multiplied with a plus b.
Perfect. You should remember that from maybe sort of lower level. That's just difference of two squares. Square number, take them away, factorise it like that. Okay, slightly trickier then. What about, let me move it over here, a cubed minus b cubed? I'll give you a clue. Like they always start with a minus b.
A minus b times a squared plus 2ab plus b squared.
It's not 2ab, it's just ab. Good, but yeah, good. Okay. All right, let's keep going. What about a to the power 4 minus b to the power 4? Does anybody know? Okay, it is in the notes, you're dead right. So go on then, read it out. Like that? Okay. Let's have a look. It's all about patterns. Okay, it's all about patterns. Can anybody think or can anybody look? What would a to the power 5 minus b to the power 5 be equal to? A minus b, good. Yeah. Yeah. Be careful with dropping the powers too. So a b cubed, yeah, plus b to the power 4. Yeah? So what's the pattern then? What's the pattern? If I said to you, all right, carry the pattern down, if I gave you a to the power of n minus b to the power of n, so any power, what is the pattern? What do you always start with? Okay, that's the easy bit. Have a look what's happening in the second bracket though. Good, so whatever the power is, you start off with one less. So if you start off with a power of 5, you'll start off with a power of 4 in the second bracket. Okay, so the power is n, you'll start a off at n minus 1. What comes next? Good. Times b plus, yeah, n minus 3 b to the power of 2 plus, let's keep going, let's just skip a few terms to the end. Would you be happy that at the end we will just get, and let me see what I've written down in the notes so I know how many to do. Yeah, you will just get a squared b to the power of n minus 3, yeah, plus a b to the power of n minus 2 plus b to the power of n minus 1. What's literally happening here, if you have a look, the a's and b's are doing opposite things to each other. So the powers of a are decreasing, they're climbing down. A to the 4, a to the 3, a to the 2, a to the 1, and then just an a to the 0 hiding there. But the powers of b are doing the opposite, they're climbing up. So you start b to the power 0, b to the power of 1, b to the power of 2, b to the power of 3, and then you finish off at b to the power of 4. So they're kind of doing opposite things to each other. One's going up, one's going down. Do you all see that? Okay. So bear this in mind, because this is going to come in handy. All right, I'm going to change this definition just ever so slightly, so bear with me. Let me create a bit of space up here. Think about where this came from. I literally said, here is a function. Okay, so here is my function, and I'm just going to draw it in like this. So y is some function of x, okay? And then I said, suppose that I want to work out some random point. So I'm talking generally, okay? This is just some random point. Now I'm going to tell you a little bit more about the function. The function is just going to be some power, okay? So it could be x squared, could be x cubed, x to the power of 4, it doesn't matter, okay? It doesn't matter, okay? So what I'm now going to do is I'm going to think about the point which is close to it. Before, with this formula, I define the point which is close to it by h, just some distance. But what I'm going to do now is I'm going to say it's a completely distinct point, because it is, isn't it? So I'm just going to call it c. I'm just going to call it c, okay? So therefore, let's think about this. If I'm looking at this point here, this is the point which I want to work out the gradient at. What must the y value be? What must the y value be?
X over n.
X to the power of n. Good, because my function is literally just raise your input to the power of n. If I look at a point which is close to it, c, okay, what must the y value at that point be?
C over n.
C to the power of n. Perfect. Okay. Now are you happy that I can think about my change in y and my change in x slightly differently? So it's slightly different to this. So let's think. First of all, I need to think about this limit. Okay. The point of this is, I want to make the distance between them as small as possible. Well, I don't want to change x. I don't want to change x because that's the point which I want to work out. So what am I going to move? I'm going to move c closer to x. So my limit is literally move c close to x. Move it as close as you possibly can get away with without it being on top of each other. Okay? Okay, now I can get rid of my change in y because it's going to be slightly simpler now. What is my change in y going to be? Perfect. C to the power of n minus x to the power of n. It's literally that, take away that. Okay? What's my change in x now? Perfect. C minus x. Okay. Okay. Now this is looking a little bit closer to this. Okay? Have a look at the numerator. Have a look at the numerator. Okay? I'm just going to deal with writing this out again. So I've got the limit as c approaches x. I've got c to the n minus x to the n. Okay? Are you happy that's literally exactly the same as that? It's just I replaced all my a's with c and my b's with x. Okay? So I'm literally just going to write this out. So I've got c minus x, so a goes to c, b goes to x. Okay? Multiplied by, okay, I've got c to the power of n minus 1 plus c to the power of n minus 2 x plus c to the power of n minus 3 times by x squared plus, right the way through, skip a load of terms, through to c to the power of 2 x to the power of n minus 3 plus c x to the power of n minus 2 plus c n minus 1. Does that make sense to everyone? Good. And I'm still dividing by c minus x. So far, so good. Can anybody see any cancellations at this stage? Good. I can see a factor which I can cancel off. Okay. So in other words, what I'm going to be left with, is the limit as c approaches x of this entire right-hand bracket. So I've got c to the power of n minus 1 plus cn minus 2 x plus cn minus 3x squared plus right the way through to c squared x n minus 3 plus c x n minus 2 plus c n minus 1. Okay, any more cancellations or simplifications that I can make with the bracket?
Is that x and minus plus 1?
Yes, it is. Thank you. Yes. Thank you. Okay. Okay, can I make any more simplifications with this? I don't think so. I've done all my cancellations. I can't do anything more. So now all that's left to do is take the limit. The process to take the limit is simply to say that c will approach x. Okay, so c approaches x. So in other words, whenever you see a c in here, you should replace that with an x, because c is approaching the value of x. Remember, it never quite reaches it, but it gets relatively close. In fact, close enough that it can behave like x. That's literally what's happening. The c approaches the x, okay? So whenever you see a c, we just need to replace it with x under the condition of a limit, okay? So, okay, there's a c, so I'm going to replace that with an x, okay? See another c here, so I'm going to replace that with an x, so x to the power of n minus 2. There's an x there, that's fine. Plus, then a c here, so I'm going to replace that with an x, okay, and then I get x squared. Plus, right the way through to, remember every c in here also gets replaced with an x. See another c there, so that gets replaced with an x. So I've got x times by x to the power of n minus 2, and that x to the power of n minus 1. Okay, so let's have a look at this then. Well, look, we know our laws of indices, so we can see what's going to happen here, right? So we get an x to the power of n minus 1, that stays there. So we're just going to simplify. But look here, okay, we've got an x, in the next term, we've got an x to the power of n minus 2 multiplied by an x to the power of 1. So we know when we have the same base and we're multiplying the two things together, we should just end up adding the powers. That's just laws of indices, right? So we get x to the power of n minus 2 plus 1. Well, n minus 2 plus 1 is x to the power of n minus 1, okay? Let's have a look on the next one. So we get x to the power of n minus 3 multiplied by x squared. Again, we should just add those powers together. N minus 3 plus 2 makes n minus 1, okay? And in fact, every single thing in here, because when you add the power of what was c, so the new x to the power of n minus something, this power here will always be one less than whatever you're taking away, okay? So in which case, when you end up adding them together, you're just going to get x to the power of n minus 1. And right the way through, and we can verify this happens over here. You've got x to the power of 1 times by x to the power of n minus 2. That should be x to the power of n minus 1. End up adding the powers. And we've got an x to the power of n minus 1 here. So effectively, we're just adding together loads and loads of x to the power of n minus 1. Well, the question is, how many of them? How many of them? Well, if you think, for example, when we had a to the power of 5 minus b to the power of 5, we end up with 1, 2, 3, 4, 5 terms. So in other words, in this bracket over here, there were n terms, there were 5 terms, which means that we should be left with n terms over here. Okay, n terms over here. So effectively, we're just adding x to the power of n minus 1 n times, however many there are, okay, because we end up with that. So therefore, it should be n multiplied by x to the power of n minus 1. Does that make sense? N times by x to the power of n minus 1. So let's have a look and see what we've done here, okay? We started off with a function that looks something like x to the power of n, okay? So y equals x to the power of n, okay? And we then proved, using this idea of limits and this idea of a binomial kind of expansion, we proved that the derivative, so dy by dx, okay, the derivative of this thing, using first principles and using the idea of a binomial expansion, should be equal to this. So dy by dx should be equal to n lots of x to the power of n minus 1. So this is the result which, if you looked up in a book or if you looked up on the internet, this is probably what you see. If you end up with a function which is x to the power of something, okay, when you differentiate it, the rule is that you should bring the power down, hence we get an n there, and reduce the power by 1. Reduce the power by 1.